Lithium batteries have become very popular in recent years. These batteries are perfect for storing higher energy level with a very small footprint. But with this immense power, there is an element of risk lurking. Now that I got your attention, we are not going to build a battery management system for EVs, which is overkill for beginners, and building that in EasyEDA would be quite challenging and very difficult. So instead we are going to look into how to build a battery management circuit for consumer electronics like MP3 players, wireless devices and other electronic gadgets. Consumer electronics oversimplify the working of lithium batteries for user experience. You see, they just don't follow a linear progression from 0 to 100 and back to 0. Instead, when the battery is fully charged, it boasts a voltage of 4.2 volts, and when it is discharged, it drops the voltage to around 2.5 to 2.7 volts. Now, why do these voltage values matter? Lithium ion or lithium polymer batteries have a higher energy density, and this voltage level tells us the energy level of the battery. So whenever we are planning to use one of these batteries in the circuit, we need to make sure that the battery doesn't overcharge above 4.2 volts or over discharge below 2.5 volts. In case if it goes over 4.2 volts, the battery temperature might shoot up and possibly explode at some point. And if it's below 2.5 volts, the battery will completely drain and lose its ability to charge again. So it's very crucial to monitor this while charging and discharging lithium batteries. Along with monitoring these values, we should also make sure the battery doesn't short circuit or pull current greater than the rated current, because this could increase the temperature of the battery significantly and reduce its lifetime. With this simple understanding of lithium batteries, we can come up with few parameters for a BMS design. For few applications, this should be sufficient. We can connect the circuit directly to the output of the BMS, considering we only have to add a voltage regulator and the circuit needs only 3.3 volts. But this method is very inefficient, and some applications need voltages up to 5 volts to operate. In that case, we need to have a buck or a boost converter for voltage conversion to use the battery more efficiently. There is a lot more to battery management apart from this, like having a fuse, monitoring individual cells in series, current sensing, temperature sensing, and auto cutoff after charging. We don't have to rush into all these features at once and look into these in the future videos. Here we can build individual circuit for each of the parameter using discrete parts, but it's very inefficient, time consuming, and expensive to do so. As an alternative, we can quickly rig this up using a TP4056 module, which provides a required battery protection and a MT3608 boost converter to convert the battery voltage from 3.7 volt to 5 volts. It works, but it seems like a lot of part once we break down the components in these modules. So after some research, I found this part, IP5306, which has all the functionality that we need. At the same time, it's easy to integrate and has an inbuilt battery level indicator. I did find more alternative components, but this IC was significantly cheaper, easier and simpler to use. If we pull up the datasheet for this particular IC, we can see all the protection it offers, along with some more features that are more advanced than TP4056 and the parameters that we discussed. Sorry to interrupt, just a side note. If you enjoyed this video so far, make sure to hit the subscribe and the like button, which will really help us make more similar YouTube videos. We have the components selected now, but how do we figure out the circuit around this IC? And what additional components do we need? To get answers to these questions, jump back into the datasheet and search for the application diagram, which should give us the minimal setup that we need to use the IP5306. Since we know what components and connection we need for the IC, let's dive deep into EasyEDA to build this. Open the sheet that we created in the previous video. Here let's start with adding the main IC. So go to the library here and search for the part we need, IP5306. You can see it directly pulls up the symbol from LCSC along with its cost and stock availability, which is super handy if you decide to import the parts or assemble your PCB within JLC PCB. Anyway, now to add the part to the sheet, just double click on the part and then left click to place it on the sheet. And to exit the component placement tool, just hit escape on the keyboard. This is the only uncommon component that we had to find for the circuit. The rest of them like capacitors, resistors and inductors should be easily available in the common library. Just click on the component that we need and click on the schematic sheet. If you like to rotate the component, you can just press the letter R. And you can press the escape key to come out of the component placement tool. Now with that, I'll quickly add the rest of the components in appropriate places according to the application diagram for easier connection. With this, we can move on to connecting the components together. First, select the wire tool from the wiring tool window. Or you can just use the shortcut W. Then select the pins with a left click and connect to the next pin that you'd like to connect. We can also change the direction of the net by just doing a left click and also stop the net with a right click whenever necessary. With that information, I'll quickly build rest of the circuit using the application schematic as a reference. Here you can see I'm ignoring the key feature, so I have a pin hanging. This could confuse both us and the EDA when the circuit gets complicated. So I'll use the no connection flag from the floating window and place it here. With this, we can save the file with Ctrl S. Now go to the design manager and see how many components and nets we have added to the circuit. We can understand most of the things in the components folder, but it's very complicated to understand what's happening with the nets. So to clean this up, we can use the net label tool and give names to these nets. Once you have given the names to the net, you can hit the small refresh icon in the design manager to see the changes. This net label not only reduces confusion, but also it helps in avoiding overlapping nets by separating them into different modules. There are more tools in the floating window, but few of the tools are just duplicates, like these power nets, which are also available directly from common library. Apart from this, we have the voltage probe tool, which is used for simulation, group tool for grouping components together, and finally, bus and bus entry tool for more complex circuits. Maybe in a future video, we'll dive deeper into these tools for better understanding. Next, let's add the value to the component. Just select the component you need and double click on the value. And on the pop-up, we can enter the value that fits our circuit. I'll make sure I do this for all the components in the schematic. Anyway, this completes the electrical part of the schematic. But we need more information and details on this documentation if you're planning to share it with a team or make it open source. To do that, we need to make the circuit look nicer by using the drawing tools. Let's start with editing the document size. Once that's set, I'll change the value on the document sheet by just double-clicking on the item and renaming them. And to add a border to the circuit, we can either use the line tool or the rectangular tool. Just select the tool, click on the area and start drawing. Once it looks good, just do a right click. We can use more drawing tools and personalize the schematics much better. And most of the tools here behave just like they should, according to the icons they have, like Bezier curves, arcs, arrows, text, drawings, polygons, circle, and pie. But I'm not going to use any of these except the text tool, since all this comes under personal preference. Instead, we'll just focus on adding a logo to the schematic using this image tool. Finally, these two bottom tools can be used to move the circuit or set the origin of the document, which is pretty rarely done. Now, if you like to customize more, each of these tools and elements has its own properties that you can play with to highly customize the circuit as you like. We can remove the grids, change the color of the nets, change the text color, and much more. Anyway, that's it for this video. In the next video, we'll discuss more about how to create our own symbol for EasyEDA in case you don't find your part in the library list. So make sure you subscribe to our channel, and if you have any questions so far, please drop them in PCB Cupid Q&A section. Until the next video, keep learning and keep creating.